from there, we're going to go ahead and know that our distance is 0 because it's going to hit the ground. Now, this is going to equal our initial velocity, which we don't know what that is, multiply it again by 6, okay? But then we're going to have the effects of gravity. So this next part is going to be, well, I'll leave it as a plus for now so you can kind of see what I'm doing. It's going to be 0.5 times negative 9.81 because gravity's pulling you down, and then multiplying that by 6 squared, okay? And then our plus or minus y at the end is going to be 0. So now we're going to go ahead and factor that real fast. So we still have 0 equals v sub o times 6. And now this will be minus 4.905 times 36. And then we're just going to drop the whole minus 0 because it doesn't matter. So we're then going to go ahead and add 4.905 times 36 to both sides. So we're going to have now an equation of 4.905 times 36 equals v sub o times 6. So now we'll divide both sides by 6. So we've got 4.905 times 6 equals v sub o. And so now that gives us a final number of v sub o equals 4.905 times 6, which is going to give us just shy of, thank you, Kristen, just shy of 30, 29.43 meters per second. Is our vertical velocity. Okay. So we've got our horizontal and our vertical velocity. Now remember, we've got a right triangle here. So since we have a right triangle, we've got the good old a squared plus b squared equals c squared. And we're obviously trying to solve for the hypotenuse. So that means we're going to now have effectively 66.67 to the second power plus 29.43 to the second power equals the initial velocity squared. Okay? So what do we come up with there? Great job, guys. So they obviously took the square root of that. So overall, our initial velocity is going to be equal to 72.88 meters per second. So now we got to figure out that release angle. And that's where we're going to go ahead and use our trig. Specifically, we're going to go ahead and we can use our tangent because we've got our opposite and we've got our adjacent. So the opposite in this example is going to be our release, our vertical velocity. And then our horizontal is going to be the other side. So really our angle of release is effectively going to be the equation of the tangent of the angle equals 29.43 divided by 66.67. So bringing over the handy dandy calculator, if I go over here and then I go 29.43 divided by 66.67 equals, and then I go trig, second, inverse, tangent. And it's an angle of 23.81 degrees. So Josh, let me make sure I write this down before I forget. Okay. So what we did is we had that horizontal velocity here, Josh. So we take 66.67, square it, plus 29.43 squared, because remember your order of operations, that's what'll get you every single time. So if I bring this bad boy back on down, okay. So, yay, so I did it again, that's kind of funny. And then I took the tangent of that, so it makes it even wilder. Okay. That's not the right answer. So instead, let's go 66.67 times 66.67 equals, and then we're going to take 29.43 times 29.43 equals. So then we're going to add to that number the 4,444.889. And so from there, we're going to take the square root of that number. And that's what gives us the 72.87. And then notice through rounding, that's where Sam came up with the 72.88. And Kristen, you'd still receive full credit. I'm not going to take off her 100th being different. Does that answer your question, Josh? Yeah, no worries. So the angle of release. Okay, so we're going to have, and actually, now I'm going to do it. We'll do it a couple different ways so you can kind of see some different slices you can do. Okay, so we've got that 29.43 divided by 66.67. So come back over, 29.43 divided by 66.67 is going to give us this value. Now, this value is what we're using for over here, and I know it's really small, where it says tangent of the angle equals the opposite over the adjacent. The adjacent is obviously the horizontal velocity in this example. The opposite is going to be the vertical velocity. So from here, I'm going to go trig, hit second, because I want to go to the inverse tangent, because I'm working my way backwards, because tangent of this angle is going to be equal to the 0.44. So hit inverse tan, and that's where I get that 23.8 degrees. So, but let's go at it from a different direction, okay? So we'll clear that out. Now, let's go ahead, and we know our horizontal velocity is 66.67, vertical is 29.43, and then our actual hypotenuse is 72.88. So let's go and we'll do the inverse of sine, because we can see sine equals the opposite, the side of the triangle, over the hypotenuse. So let's go ahead and we're going to take effectively 29.43, divide that by 72.88, and we're going to have a little bit of, rounding changes, and that's fine. So we've got this number, second inverse sine, 23.8 degrees. Notice. Remember, Anouk, every single time we're using anything projectile motion on this planet, we're always considering gravity to be at 9.81 meters per second. If I purposely give you guys an example, and we'll do that. We'll do one that's on the moon for fun. The 36. That's because remember, it is going to be time squared. So it's t to the second power. So whatever the time is, it's not 6 seconds. It's not multiplied by 6. It's multiplied by 36. That's how I went from up here. That's why you see negative 9.81 times 6 to the second power. That's what the caret is meant to be, where it's going up. So it's being exponent. And so that's why when we convert over the next one, you've got, I combine the 0.5 and the negative 9.81 to get 4.905. And then obviously 6 squared, 6 times 6 is going to be 36. That's how I came up with that, Lexi. So yes, gravity is always going to be pulling you downwards. If all of a sudden gravity shot us all up, that would be moderately terrifying. Yes, unfortunately, gravity is dragging us all down all the time. So now the last way to slice it, just so you guys can see it, is we take 66.67, divide that by 72.88. Okay, we get that number, then we're going to go trig, second inverse, because now we're going the adjacent, so our horizontal velocity, divided by the hypotenuse. So we're going to use cosine as in ca, C-A-H. So you get cosine, notice again, 23.8 degrees. Boom. So that's how we use those functions effectively, or a way that we can use it to infer things when we're going backwards. Now, the other thing to keep in mind, guys, when you're using the sine or the cosine, remember it's always going to be the opposite over the hypotenuse. And cosine and sine is all based around effectively 1. So the cosine of 0 degrees is 1, and then the sine of 0 degrees is 0, because it's just a 1 distance radius circle. So that's why, cosine and sine of 45 are equal, because it turns out 45 degrees, those numbers are going to be the exact same. And it's going to be then creating a right angle triangle. And remember, with triangles, a squared plus b squared is always going to equal the hypotenuse, which is c squared. So that's why you're going to get these numbers that are always, essentially 1 or a certain fraction of 1. Whereas tangent is going to be effectively our y value, the sine, over the adjacent. So that would be the cosine value. So that's why those numbers can get massive and then obviously become unrealistic at certain angles.
Can I ask you something?
Yeah, what's up?
Okay, so you had eventually 6 squared, so then you had 4.905 times 36, but then under that it says 4.905 times 6. How did you got that?
Say one more time, Anouk.
Well, first you have like 4.905 times 36, and then under that it says 4.905 times 6. So
okay, yes. So notice, okay, so we go from here where we've got 0 equals v sub o times 6 minus 4.905 times 36. Then we're going to add 4.905 times 36 to both sides. So now notice now we have 4.905 times 36 equals our initial velocity times 6. And so then we're going to divide both sides by 6. So we're left with 4.905 times 6 equals our initial velocity. So obviously it's a problem with typing it out as opposed to where you could see me actually cross things out, erase, and move numbers around. So you can kind of see how we're factoring. If you're thinking back to algebra for you guys. Yes, Colton, remember every single one of these is up here. That's why it's got the equation slide that I want you guys to use on every single different quiz that you guys take. Print it off, have it next to you as a scratch sheet, or just have it open. I have no interest in you guys memorizing formulas. I have every interest in you knowing how to use the formulas. And Josh, we just worked through effectively how we came up with the 23.8 degrees with every single different trig function that we'd use in this class. Because remember, if you come down here, one example is this way. We can then have the sine of the angle is going to be equal to 29.43 divided by 72.88. And that was equal to 23.8 degrees. And then the cosine of the angle equals 66.67 divided by 72.88, which is also going to equal to 23.8. Just remember, guys, when you're doing these problems, you have to hit the inverse sine function. So that's where the actual function itself is going to, in order to get, okay, so let's factor this one a little bit further. Okay, so what we then need to do is we take the sine of the inverse -1 is equal to the 29.43 divided by 72.88, close, and then that's going to be equal to the angle, which is equal to 23.8 degrees. So let's go ahead. I'm going to have you guys get in groups, and we're going to do 2 different projectile motion equations. Okay. The first one we're going to go ahead and do is, we're going to have a little fun. Getting ahead of myself with group members. Okay. So you guys are going to be randomly assigned, obviously, into 4 separate groups. I'm putting up into the chat this exact right up here, so you're going to be able to see what I'm talking about. Now, if we bring this bad boy down, we can actually see good old results for gravity on other planets. Well, let's just see what we come up with here. Boom. So now you can see the acceleration due to gravity. So see, Earth, 9.81. Venus is going to be less. The moon is way less. Mars is pretty solid less. Jupiter is, you are going to feel real heavy. So your horizontal velocity for all of these is going to be the exact same. The key difference is going to be your vertical velocity is going to be very different. So remember to factor it like we did before. We just did. Can I paste in a picture? No, I can't paste in a picture. That's too bad. But find the horizontal and the vertical velocity, then the initial velocity, then do the trig for the angle of release. Okay? Questions, comments, concerns before we put you guys into 4 random groups? Okay, it's 9:58. Let's give you guys a good 10 minutes to work your way through this. And then we'll see how it went. Okay? Have fun. Get after it. So here's the next formulas that we worked on in class for a little while. I obviously forgot to hit record while we went through the data. The groups did a good job of making sure they found out, obviously, the release angle. And from there, we were able to determine that you're going to hit your peak height at effectively half of your flight time in the examples where you start on the ground and end on the ground. So if there's no vertical change, you're going to go ahead and hit that highest point at half your flight time. Now they're working on the obvious question that's highlighted below, working in groups with obviously the information of the acceleration of gravity and then the order of operations, where they're going to go ahead and figure out first the horizontal and the vertical velocities. And then from there, they're going to use the vertical velocity formula and the quadratic equation to solve for what would have been this flight time. Then they're going to take half that flight time, run it through the vertical distance formula using the acceleration, obviously, for the planet that they were given as a group. And from there, they're going to obviously have the highest pointers off the ground. And then finally, they're going to use the horizontal distance formula with that full flight time to figure out how far it would have flown during that period. So using the good old trig equations to obviously figure out what was going to be the horizontal and vertical velocities that they're going to have had. And then obviously we're going to see that the planets with the highest gravity is going to have the shortest distance it would have gone, whereas the planets that have the greatest, the lowest gravity, they're going to have gone the furthest distance. So we did have one group when they were going through and working on the trig, they inverted their values. So instead of it being a very flat release, just because it was fired a really high trajectory for the previous question, they had it more like 87 degrees. So they just used the wrong essentially function in trig. And because of that, they just flip the values. Whereas if they would use the correct one, then they would have had the right answer, which for them was about 2.8 degrees. So good luck, guys, if you're doing this on your own, and hopefully you're having fun with these examples. All right, guys, what did you guys come up with? What did you guys come up with for your answers here? Okay, Anouk, which group were you in? Obviously, that's giving us the flight time. Ah, yeah. Damn. Makes sense. Obviously low gravity. So guys, think about it. 1,326 meters is the equivalent of, it's more than 3/4 of a mile vertically. And then the horizontal travel, 9 kilometers. So we're literally talking about going, yeah, just a paltry, 5 miles or so. Nice. What did the other groups come up with? No. So Taylor, good. Remember, the ball starts on the ground. So you're always going to get a 0 value in these equations when you use the quadratic formula. So it started at the ground on 0 because that's what we talked about. So the next number you're going to use is that 123.46 seconds it would have spent in the air. So now you would take half of that 123.46, and that's going to be the point at which it was the highest off the ground. So you run that through the vertical distance formula with the acceleration of gravity on the moon, and it's going to tell you what the highest point is. And then you're going to take that full time of 123.46 and multiply that in the horizontal distance by that horizontal velocity of 173.21. And now you've got effectively how far it would have gone over that time period. So that's okay. Good job. You guys got through the quadratic equation, and that's the hardest part of it. Yeah, I can work through it. So let's, where do you want me to start from? Yeah, that looks, you're definitely on the right spot. So then you take, and your vertical, so the highest point, that's okay. So you're going to take what would be 11.275, because that's the half distance. Yeah. So let's go ahead and let us start at the beginning, for that is always a good place to start. So because I like life on hard mode, we're traveling to another planet from mine. Let's go with Neptune, because it's going to be cold as hell and it's got a lot of gravity. Okay, so first thing we have to do from just looking at the formula in general, so if we're working from Neptune, is we're going to go ahead and figure out our horizontal and vertical velocity, which is going to be the same for all the groups. So we got a vert velocity of 100, a horizontal velocity of what's going to have been that 173.21. Okay, so now we need to figure out that vertical time. So we're using the vertical formula, and I'm just going to fill it in as I go. So 0 equals our 100 times time. And then because gravity is always pulling us down, we have negative 0.5 times 14.07 times time squared, and then plus 0. So effectively, the way that this makes everything out to be now, sorry for changing up the frame of reference quite frequently, but it's probably going to be more useful, is effectively what we have here is this is our B term. This is going to be our A term. And this is going to be our C term if we, or when we put it into the quadratic formula, okay? And so 14.07 times 0.5 is going to equal negative 7.035. Okay. My B term is going to be equal to 100, and that's positive. And C is 0. So it's a little more lined up. So now we have our quadratic equation. So the first part is we have on top, which is going to be negative b. So we have negative 100 plus or minus the square root. So we open new parentheses of 100 squared, okay, minus 4 times 7.035 times 0. Okay. And then all of this, because we're going to close this out so it makes sense, is going to be divided by 2 times negative 7.035. Okay. So let's factor this out some. So now we have negative 100 plus or minus, okay. Now, 4 times 7.035 times 0, anything multiplied by 0 is 0. So we can just drop that out. So we have 100 squared, and then we take the square root of that. So the 100 times 100 then becomes 10,000. The square root of 10,000 is 100. So we have plus or minus 100. Okay. And then all of that divided by negative, okay, 14.07. So that's going to give us two solutions. We have one where it's negative 100 plus 100, so 0 divided by negative 14.07. And then we have another one, which is going to be equal to negative 200 divided by negative 14.07. So by the nature of the beast, these both become positive because a negative divided by negative is a positive. And then this is going to give us our time value we really care about. So pull up our handy dandy calculator, take 200 divided by 14.07, and we get 14.214. 14 point, we're just going to go 21 seconds. Okay, that is our total flight time in this example. Okay, so now we can start solving for these equations. So the first one, to figure out the highest point it went, well, we're going to take half of that flight time. So now this equation up here is what we're going to start off, but for t, we're putting in half of 14.21. So we get effectively our x equals 100 times 7.105 minus, okay, let me give space so it gives us a little more space to follow it, 0.5 times 14.07, and then times 7.105 times 7.105. So you can see it's literally squared, okay? And then plus 0. So then we again are going to go ahead and bring up our handy dandy calculator. We're going to clear that out. And we're going to take 0.5 times 14.07 times 7.105 times 7.105. That's going to be equal to 355.134. Okay. Now we're going to be 100 times 7.105. So we literally have 710.5 minus that 355.134. And so from there, we have a peak height of 355.366. So then our horizontal velocity, so our horizontal distance is going to be equal to 173.21 times 14.21. So clear that out, 173.21 times 14.21, that's a happy little coincidence. So we've got 2,461 meters. So that's how you break down each part of this equation, going from our initial factoring to get ourselves into the quadratic formula. From there, we're going to go ahead and run things as we go. Now, the only other addition that I obviously kind of skipped on, which would have been if we take that 30-degree angle. So we'll go ahead and we'll just cover that real fast so you guys can see it again. So since it's a 30-degree angle, which means it's got a lot more horizontal than it does vertical, we're first going to get the vertical velocity. So we use the sine. So we're going to have the sine of 30 equals the opposite divided by 200. So what we then do is we multiply both sides by 200. So we have 200 times the sine of 30 equals our horizontal velocity, and that's where we come up with 100 meters per second, because the sine of 30 is literally exactly 0.5. And so for the cosine of 30 is going to be equal to our adjacent divided by 200 again. So we're going to then go 200 times the cosine of 30 equals, my God, I'd be dangerous if I put in the right horizontal velocity, because that's our adjacent. And that's what's going to give us that 173.21 meters per second. Sine is the opposite, so that's the vertical. Cosine is the adjacent, so that's the horizontal. Wow, guys, it's a snow day. We were only supposed to go for an hour, and we've almost gone for the full hour and 15. Way to be overachievers. I like that. Any other questions before we go ahead and wrap up? And then next week, we're going to be getting into chapter 3.
Can you scroll down a little? So I can see like the calculations. Okay, thanks.
No worries.
Is there any way that you could type in like an example question that I can work on after the lecture? See if I can figure out.
Yeah, no worries. So I guess we'll make it the take-home assignment for you guys is throw out some random stuff that's just awkward and not that random. And from there, Colton, pick a planet, any planet. Oh, let's just go with the Earth, just so you guys can all try to do that. But you guys could run it on the other planets if you want. So, hey, no worries, guys. The more we work through this together, and the reason I put you guys in your breakout rooms is because you guys have a chance to, and I do mean this in a positive way, struggle together. If you guys immediately get into the groups and you're like, I have all the answers, then it's not helping you as much, because I could run through these examples all day long. But if you guys have to sit down, interact with it together, hit those walls, and eventually find the way to break them down and get through them, you're going to understand it, you're going to be able to apply it. So, Colton, you got the right attitude, as do all of you guys, which is, we need to practice. We need to try this on our own. It's okay to fail. Like, that's the goal, is that you guys are going to keep trying, failing, but you're going to get a little better each time until you're going to obviously figure it out. You're going to understand it, and then you're going to be acing it. So yeah, guys, don't get discouraged. This stuff is not easy. A lot of you guys have never had physics, math and stuff and otherwise, and this is the application of it. So, but this is the foundational stuff of learning how to play with these numbers and see how they all intertwine. So stay safe out there, guys. If you do any fun sledding, make sure you do social distance, but let me know how it goes. If you guys are on campus and you guys want a decent hill, but I don't know how safe it is to go down, you guys should go check out the Taylor Fork area, which is like way past the wood chip trail, past like where Fire Science is. That hill is steep. Like I run up it for training, so I imagine sledding down it would probably be a good time. So anyways, guys, stay safe out there. Great job today. See you guys later.